Okay, now that you know that, we're gonna move on. The topic for today is how to find or to determine the components of a vector. There you go. That's what we're going to do today. We're going to talk about how we find the components of a vector. This is the most mathematical part of this topic, because we're going to be dealing with some things that you probably already know, and some new things in maths. I don't want to freak out. It's just some basic application. It's basically your calculator will be doing the important part of the process, so you don't need to worry about this being too complicated. Okay, I think you remember from the animation that we worked with the last class how vectors can be represented in a set of axes. Remember, we had an x-axis, we had a y-axis, and in that simulation we had a vector that I'm going to represent here with this red arrow. That vector is, in this case, we're going to call it A. Remember, this symbol here is an arrow that we put on top of it, just to say that A is not a regular scalar, but it's a vector, so it has a magnitude and it has a direction. Together with the vector, if you remember, we had two other things. We had its components. So we had a green line that was representing how long that vector was along the x-axis. Sorry, today I'm just going to add this to say that this line is not a regular line, that is actually another vector. So this vector, or this component, is what we call AX. This X is to represent, that is the X part of vector A. And the other component, which goes along the y-axis, something like this, is what we call AY, meaning that is the Y part of the A vector. The other element that we discussed was the angle. This angle is represented with this letter that is taken from the Greek alphabet. That letter is called theta. So the symbol is just like an O with a line dividing it, and you write it like this: T-H-E-T-A, theta. Okay, that's just for you to know, because it's a new symbol maybe for all of you. So the deal today is we're gonna be learning how these elements are related, how the magnitude of a vector, the angle, and the size of the components are related. And the first thing that we're gonna do is we're gonna learn how to use the magnitude of the vector together with the angle to determine the size of the components. Then we're going to do the opposite. We're going to see how we can, from the components of the vector, obtain the magnitude and the angle. So I want you to draw this, to have this diagram in your notebook, because this diagram is going to be very important to explain the maths of how we do it. Now, before we actually understand how that is done, we're going to learn and remember, because probably you already know this, a couple of things that are basically mathematics. Okay, So we're going to do that, and then we're going to move to this topic. Okay, before we can move on, there's something we need to check, and it's about your calculator, your scientific calculator. This is a calculator probably similar to the one you have. The first thing that you need is look on top of the screen, on the top area of the screen. I don't know if you see, but here there's something, right? That is a letter, and that letter should be a D as in Diego. If the calculator says D, then that means that it is configured correctly, and that D means that the angles that we work with will be measured in degrees. Because all the angles that we're going to work with are in degrees, we need a D to appear there. Now, if you cannot see a D there and you have another letter, then you have to hit the mode key, which is right here or somewhere in your calculator up here. When you hit that key twice, it will take you to 3 options: 1 for degrees, 2 for radians, and 3 for gradients. Those 2 are just other units for measuring angles. So because we want degrees, I'm going to select option 1. And if the D was not there, now you will see the D up here in the screen of your calculator. So if the D is there, that means that you're ready to work with angles in degrees, and that's good because that's the unit that we're gonna be using. Okay, so once you check that, you know that you're ready to keep going. Okay. Now, the next thing is to also use your calculator to find something that we call the sine and the cosine of an angle. Just let me write it for you. We're going to be working with two concepts in mathematics that are called sine and cosine, right? Sine and cosine are something that you can use together with an angle to obtain a value that in this case will be used to determine the components of the vector. Remember that that's what we want to find, how long this green line and how long the blue lines are. So in your calculator you will not find this word sine, but you just will find S-I-N for sine, and for cosine you will just find C-O-S. And probably you can see that there are some, I don't know, I don't think you can see it, but they're here, sine and cosine. So we're going to be using those two. Remember, your calculator needs to be in degrees. How do you use those? Well, basically to use sine or cosine you need an angle. So if I give you the angle 60 degrees, then that means that you can use your calculator to find what the sine of 60 degrees is, right? You don't know that. Or you can use it to find the cosine of 60 degrees. The sine and the cosine always need an angle, right? If you don't have an angle, there's no way you can use sine or cosine. This is not something that you need to memorize or anything, because the calculator will do it for you. So if I want to know what the sine or the cosine, I'm just gonna write this, exactly this. I'm gonna write sine 60 degrees, right? And when I have that in the calculator, I will just press the equal sign, and it's going to give me the value of the sine. In this case, okay, you see there, the sine is 0.866. Well, it has a lot of decimals there, but I'm just going to use 3 decimals there, 0.866. That's the sine. What about the cosine? If I need to find the cosine of an angle, out, sorry, I just do cosine of the angle. If that angle is 60 degrees, just cosine of 60, right? And that is 0.5. Always when you do a sine or a cosine, you will get a number like 0 point something. You will never get something bigger than that. You will never get 1 or 2 or 3. You always get 0 point something. So this being able to find the sine or the cosine of an angle is important, because we're going to use those sine and cosine values to be able to find the components of the vector. So what I want you to do right now is, in your calculator, find the sine and the cosine for 30 degrees and write that in your notebook, and do the same for the angle 45 degrees. So you're going to write sine of 30, no, sorry, not 30, let's work with a different angle, sine of 40, so sine of 40 degrees, and you're going to find that with a calculator just so you can see how it works, and the same thing for 45 degrees. Okay, so do it and write your answer in front of each one of those. Okay, so with your calculator, do it. I already did it, and if you want, you can pause the video right now and wait till everyone does it, and then you just keep watching and you'll see the values. Okay, I assume that you already did that, so I'm going to show you the values. If your calculator was configured correctly, these are the answers that you should have obtained: 0.642, 0.766 for sine and cosine of 40, sine of 45, cosine of 45. 45 degrees is like a special angle, because the sine and the cosine for that angle, they have the same value. Right now, some of you may be wondering, what is that sine and cosine? And I know it's something that you would like to know to understand a little bit better why we're doing this. But because this is not a mathematics class, we're not going to be studying that here. We're just going to learn how to use those values. Okay, we're going to use those values. So right now you don't need to worry about what they are. You will understand that later on when you're working in mathematics with your teacher, and you study in detail where sine and cosine come from and how to use them. Okay, so this is the first thing, sine and cosine. Now that we know this, we can move on to actually finding the components of a vector. So I'm going to erase this, and I'm going to go back to our diagram. This is the diagram that you all have in your notebook, showing the vector, the x component and the y component. So before we move on, there are two names that I need you to remember, and it's another word that we have for this component that is right next to the angle, right? You know that this angle is you can see how this y component, you can draw it here, or you could draw it here, right? So it's the same thing, it's the same distance, right? So this length here and this length here are actually the same, right? So if you compare this with this, they are the same. So I'm telling you that because sometimes the component that is right next to the angle itself, we call that the adjacent component. This word in Spanish, adjacent, is adyacente, and adyacente means right next to, right? When something is right next to other thing, those two things are adjacent. So this component is adjacent to what? To the angle. And this component, that is the same as this one, right? It's the same value. This component, it's called the opposite component. Okay, so many times we will refer to the component that is right next to the angle as the adjacent one, and the other component, the one that would be opposite to the angle here, which is the same as this one, we will refer to that component as the opposite component. Okay, so in your diagram, make sure you write those two names: adjacent for the one that is next to the angle, in this case that adjacent component is the x component, and opposite component for the other component, the one that will be in front of the angle, which in this case is the y component. So I'm just going to erase this so we can keep going with the explanation. Good. Okay, I'm not gonna give values to any of this, right? I'm just going to work with the symbols to give you a more general way of doing it. Later on, when we're working on specific examples, you will be actually putting numbers into all those things. But right now, I'm going to just work with the symbols A for the magnitude of the vector, AX for the value of the x component of the vector, AY for the value of the y component of the vector, and theta for the angle itself. Okay, so if this vector is 3 units long, then A will be 3. If this component is 2.2 units long, then AX will be 2.2. AY will have a different value, and theta will be the angle excuse me, the angle that the vector has. Okay, so here's the important thing, and this is like the probably the most important part of this whole explanation. If you want to find the adjacent component to the angle, in this case the x component, what you do is very simple. You're going to multiply two things. You're going to multiply the magnitude of the vector itself, which remember is A, right? So I'm going to multiply whatever A is times the cosine of the angle theta. Okay? When I multiply these two things, you already know how to find the cosine of an angle. So if you multiply the cosine of an angle, and then if you find the cosine of an angle, sorry, and then you multiply that times the length of the vector itself, the whole thing, the red arrow here, that will give you the size of this green component. The reason for that, again, comes from mathematics, and it's not something that we're going to learn here. We're just learning how the cosine can be used to do something that we need in physics, okay? Because we need to find the x component or the adjacent component, then we use the cosine. Now, if what you want to do is to find the opposite component, or in this case the y component of the vector, you're going to do something very similar. You're going to multiply the magnitude of the vector A times, and you will not use cosine, but you will use sine. Okay, so you multiply the magnitude of the vector times the sine of the angle, and that's how you obtain the adjacent component to the opposite component, or in this case the y component of the vector. So if I give you values, you would be able to find that, right? In your notebook you have examples in which you know the value of a, you know the value of the angle, so you can just enter those values here and work out the value of the magnitude of the components of each vector. Okay, so we're gonna move on to some examples about this so you can see how it works. And actually I'm going to work with one of the examples that you have in your notebook. If you remember, when we were working with the simulation that I sent, I asked you to draw some vectors for me, so we're gonna go back to those vectors and we're gonna use example number 1 to do this analysis and actually verify that if we do this process, we're going to be obtaining the same value for AX and AY that the simulation gave us. Okay, so let's do that. Okay, so this example that I have here is the first example that I asked you to draw when you were working the previous class with the simulation. In that first example, we had a vector with a length or with a magnitude of 8.6 units. They don't give the units here, it's not relevant right now because we just want to understand how the components work. Later on we will work with the units. So it has a length of 8.6 and it has an angle theta of 32 degrees. In the simulation they gave you also the value of AX and the value of AY. What we're going to do today is we're going to try to see actually if the values that we obtain are the ones that the simulation gave you. Okay, so let's do that. According to what we just saw, right, and that is something that it should be in your notebook, if I want to find the x component of the vector AX, what I need to do is I need to multiply the magnitude of the vector itself times, in this case because x is the adjacent, I will multiply times cosine of the angle. Okay, so let's put that in numbers. In this particular case, AX will be equal to A, which for this particular example is 8.6, so that's A, times what? Times the cosine of 32 degrees. How do you do that in your calculator? Well, actually in your calculator you can just write this whole thing. You don't need to do separate operations. So I'm just gonna show you here. What I do is 8.6 times cosine of 32, right? I just write that whole thing, 8.6 times cosine of 32, and when I get the result, it tells me that the x component of this vector is equal to, you can see there, 7.29, so I'm going to round that to 7.3. And if you go back and look at the example that the simulation gave you, the value of AX is actually 7.3. Sorry, when you do it like this, you get an even more precise value of the component. It's not 7.3, it's 7.293. Well, you have all those numbers, but we're just working with 7.3 to make just to compare to the value that we had obtained before. Okay, now what if I want to obtain not the x component sorry, but the y component? If I want to obtain the y component of the vector, I would have to multiply the vector itself times the sine of the angle. Okay, if I do that, I get that a, again, the value of a is still 8.6. That's what we had from the beginning, so that doesn't change. 8.6 times the sine of the angle, and the angle is still the same, is 32 degrees. I'm just doing sine now instead of cosine. So what do I get there? Let's do it with your calculator. You just do 8.6 times sine of 32 degrees, and when you do that you get 4.557. and if you check the value that we had obtained using that animation, that value is 4.6, because you know, if you approximate that 4.557, if you round it to just one decimal place, you will obtain 4.6. So the value of the y component of this vector is 4.6. So yeah, that's it. You see how from the value of the length or the magnitude of a vector and its angle, using sine and cosine, you can easily find the values of the components. What you need to remember is that to find x, the adjacent component, you use cosine, and to find y, the opposite component, you use sine. That's pretty much everything you need to remember, because if you look at the two equations, they're actually very similar. So the first equation that you're going to learn, or that you're going to remember, is this one, which is to find the x component, and the other important equation is going to be this one. Initially I could give you those equations for the purpose of quizzes and exams, but eventually you will end up just memorizing that. So probably in the end of unit exam I'm not going to give you that, because you will have used it you will have used it so many times that by that moment it will be something automatic. You will just know that for the x component you use cosine, and for the y component you use sine. And how do you use it? Well, you just multiply the magnitude of the vector times cosine, or the magnitude of the vector times sine, to find the magnitude or the value of the component that you're looking for. Okay. If you're having problems understanding this, remember, you can just go back and recheck and look at the video again to understand whatever you're not getting. Okay, so that's like the part of finding the components, and we're gonna move on with the next thing. Okay, this last part is about applying actually the components of a vector into something that that is more meaningful to us. So this is the title. And next thing, I wanted to try to remember the simulation that we used when we were shooting different objects to see how they moved. So again, we had a cannon here that was firing different objects, and we were studying how the trajectory of those objects was. We were studying the range and we were studying the maximum height. Now, at some point at the beginning of this section about vectors, I told you that one of the variables that we manipulated when we were working with that animation, with that simulation, sorry, was the initial velocity. Okay, so the initial velocity can be represented with a vector because velocity is a vector. So if you fire this object with a velocity of 16 meters per second, right, you can represent that with an arrow. Okay, this arrow represents 16 meters per second. This arrow, although it takes a big part of the diagram here, that arrow is just showing the initial velocity. You know that right after the object leaves the canyon, it starts changing its trajectory. So so it doesn't go like that, it doesn't keep going straight, but it curves its trajectory and it comes down to this point here. But how high this object goes and how far it travels on the ground depends on the components of the velocity of this vector. That's why we have been studying components, because if we want to understand why this object goes as high as it did or why it goes as far as it did, then we need to understand how the components of that velocity actually work. So I just have here 16 meters per second because that is the velocity that we used in the simulation, and I'm going to go with an angle. I'm just going to give it a random value. Right? Let's say that one of your angles was I don't know, 37 degrees, right? Probably it wasn't, but let's say one of your angles was 37 degrees. So the point here is that V, or let me just call it U because it's an initial velocity. U, the initial velocity of this, is 16 meters per second. But that velocity is not entirely along the x-axis or entirely along the y-axis. That velocity is like in between. So it is important that we know how much of that velocity is along the x-axis. We're going to call that ux, the x component of the velocity. And we also would like to know how much of that velocity goes along the y-axis, and we're going to call that uy. Okay, so let me just write this again so you can see the angle is 37 degrees. And what we excuse me, what we need to what we're interested here in knowing is how much of this 16 meters per second goes in the x-axis, because the velocity, the part of the velocity that goes on the x-axis is what will determine the distance that it will be able to travel horizontally. So this velocity will be obviously related to the range, and how much of this 16 meters goes in the y-axis, that will determine what happens vertically. So that means that it will be related to how high it goes. Okay, so how do we find then the initial velocity the x and the y axis for this particular example. So what we know is that, I'm just gonna write it here so you remember. If you want to find the adjacent component, what we had was this. The adjacent component will be the vector itself times cosine of the angle, and the opposite component, or the y component, will be ay will be a times the sine of the angle. So I'm just going to apply that to this example. Okay. Okay, so I want to find the value of ux, the x component of the velocity. I need to know how much of this 16 will go into the y-axis. How do I do that? It's very simple. I just multiply u, which is the vector in this case, times the cosine of the angle. So let me just put numbers into that. U, the vector, in this case this vector represents a velocity and its value is 16. I'm not writing the units, I'm just going to write the units at the end. So 16, which is the magnitude of the vector, times cosine of 37 degrees. And I'm going to do that in my calculator. The calculator says, well, 16 times cosine of 37 degrees. That is, I'm going to round it to one decimal place, so it is 12.8 meters per second. That means that when I fire an object at 16 meters per second with an angle of 37 degrees, I make that object move at 12.8 meters per second in the horizontal direction. So out of those 16, 12.8 meters per second is the velocity that the object is going to have along the x-axis. Now if I want to find the other velocity, the initial velocity in the y-axis, or the components of the initial velocity, I just do the vector itself, which in this case is u, times the sine of the angle. So u, which is 16 meters per second, times the sine of 37 degrees. And if I do that in my calculator, I get 16 times 37 degrees. What I get is 9.62. So 9.6, because I said I was going to take only one decimal place. So 9.6 is the velocity of the object along the y-axis. This analysis of finding the initial velocity in the x-axis and the initial velocity on the y-axis for this type of motion is very, very important. In an exam, I can give you a question like this one, and it will be a level 1 or 2 probably, because this is the very first thing that you need to learn, right? So this is not supposed to represent a big problem. So if you're not following this, you know, you can go back and re-watch this video, but this needs to be like very easy for everyone. Again, if you don't get it, you can use this video or just ask me or write me an email and I can clarify things for you. But the thing is that knowing how to do this will be the very first step of a much more complicated thing. Once we know the x and y velocities for this type of motion, we can start finding more and more properties about this trajectory, right? The idea is that now that we know these two velocities, 12.8 and 9.6, we know how fast the object is moving in both the x and the y axis, and we can use that information, for example, to know this maximum height here, how high it went, or how much distance it traveled along the x-axis. We can find the range, we can have we can find the maximum height, we can find the time that it takes to complete that whole thing, we can find the velocity that it has at different points in the trajectory. So this first part about vectors and components is it's like the foundation of what we will be learning later on. So make sure you get this, make sure you complete your notes. This should be in your notebook, this whole thing, because those are the notes that we're going to be using when I'm back. Okay, so probably when you're listening to this, I'm already in a plane flying like 10 hours to go back to Colombia and see you again and see how much of this you understood. I hope these videos were a better way of doing things. I'm going to try to use them a bit more because I know that it's useful to be able to check and recheck things. But I just thought that it was a good idea that in my absence you could have me somehow explaining things, because sometimes that's better. Okay, thank you and see you soon. Bye bye.